4.4 Method of Images and Introduction to Green Functions. Following conventions/notation of Jackson 32 Chapter 2. When introducing Green's functions, brief mention was made of the method of images. The basic idea is that by placing charges external to the region of interest, we might elicit the electric field and boundary conditions on the actual region of interest. In particular, this then eliminates the need for a complicated surface charge description. Consider a point charge q distance d from a mirror, conducting surface. This produces the same equipotential surfaces and field lines as having an opposite charge distance d on the opposite side of the mirror, with mirror removed. Let's consider the slightly more complicated scenario of a point charge near a grounded conducting sphere. Let's take the origin of the coordinate system to be that of the sphere. Let's place the mirror charge on the same radial line, but inside the sphere. Let's now show that if we have charge q at radial distance y, the mirror charge will be negative a, q over y, and at distance, a squared divided by y.
Charge outside a conducting sphere, potential by method of images to begin. Let's consider a point charge q in the presence of a charge, q, insulated, conducting sphere, radius, a. Using superposition, let's establish the field exterior to the sphere due to the charge with conducting sphere boundary to be charges q and q prime equals negative, a, over yq, and interior to the sphere, spherically distributed, the charge, q minus q prime, exists, such that the potential in the region outside the sphere is, equation 4-83. The radial force acting on the exterior charge is then, equation 4-84. Note that this force is attractive at short distances even if the charges have the same sign. The work function of a metal, for an electron to be removed, is in large part the work done against this attractive image force.
Suppose the conducting sphere is at a fixed potential, instead of charged and insulated, such that the potential phi of A equals V at the surface, then using mirror charge as before, equation 4-85, and force, equation 4-86. Consider next what it means to have a conducting sphere in a uniform electric field. A uniform electric field, E sub 0, can be represented, locally, by two charges equal and opposite in distance from the field position of interest. If we estimate the local field, by superposition to be equation 4-87, and allow r goes to infinity and q goes to infinity such that 2q divided by r squared equals E sub 0, we get the uniform field. Return, for the moment, to r and q finite, and consider the mirror charges, taking advantage of superposition, to establish neutralizing boundary conditions on a spherical boundary with radius a. The potential with placement of mirror charges is then, using the previous notation of reference point x vector and charge q location point y vector, and charge negative q location point negative y vector.
Equation 4-88. A better notation for this would start from x vector equals r vector and y vector equals r vector, such that equation 4-89, where theta is the angle between r vector and r vector. Then we have, see the next equation, equation 4-90, which simplifies to equation 4-91. The surface charge induced on the shell is given by equation 4-92. Green's function for space with conducting sphere. Let's consider the Green's function for when there is a conducting sphere as described previously. Now we see this is like a Green's function due to a single point charge to now include one with an image charge.
Equation 4-93. Since we are describing a conducting sphere with zero charge, we have Dirichlet boundary conditions, thus we have the formula, equation 4-94, where d, a, prime equals, a, squared d omega prime and, equation 4-95, thus equation 4-96, where, spherical coordinates we have, cos gamma equals cos theta prime plus sin theta prime cos times phi minus phi prime.
Example 4.17. Let's apply this to the case where there is a conducting sphere with upper hemisphere at plus v and lower at v. Solution. Recall the relation. See the next equation. Thus see the next equation. With general form for the potential. See the next equation. Let's arrange our coordinates such that the hemispheres are aligned with the z-axis. Then cos gamma equals cos theta prime and we get See the next equation.
Example 4.18. Jackson 2.1. A point charge Q is brought to A position at distance d away from an infinite plane conductor held at zero potential. Using the method of images, find A. the surface charge density on the plane, B. the force on the charge, C. the total force on the plane by integrating 2 pi sigma squared over the plane, D. the work necessary to remove the charge Q from its position to infinity, E. the potential energy between the charge and its image. Solution. A. Have charge Q at R sub 1 equals the square root of R squared plus D squared minus 2 R d cos theta with mirror charge AQ at R sub 2 equals the square root of R squared plus D squared plus 2 R d cos theta. The potential field is thus.
See the next equation. Let's move to the surface of the mirror with this potential field in the real, not virtual image, side, with electric field E vector sub 1 equals gradient phi, while on the conductor side we simply have E vector sub 2 equals 0, and on the conductor surface E vector sub 1 times N vector equals 0. Using the pillbox formula, N sub 1 dot, E vector sub 1 minus E vector sub 2 equals 4 pi sigma, we get, see the next equation. See the next equation. See the next equation. In polar coordinates, see the next equation. And making use of n vector dot e vector sub r equals cosine theta and n vector dot e vector sub theta equals sine theta.
See the next equation. See the next equation. Thus, see the next equation. B. F equals negative QQ over 2D squared equals negative Q squared over 2D squared N, attractive. C. It is claimed that surface energy density is W equals 1 over 8 pi. The absolute value of E squared equals 2 pi sigma squared. Let's start by showing this. Recall that see the next equation. Thus, using W equals Q phi with the superposition of charge fields, with see the next equation. Individually and see the next equation. In total. Or, if charge distribution continuous rather than discrete, have. See the next equation. See the next equation.
The integration across the mirror surface to get the total force acting on the plane is then straightforward. See the next equation. Let's use ρ equals d times sin h of x. See the next equation. D, w equals negative the integral of f of dx equals the integral from d to infinity of q squared over 4x squared dx, and we get, see the next equation. E, w equals 1/2 the sum from I2 of the sum from j2 of q sub I q sub j over the absolute value of x sub I minus x sub j equals 1/2 the sum from I2 of phi sub I q sub I, and with q sub 1 equals 1, q sub 2 equals negative q, phi sub 1 equals negative q over 2d, phi sub 2 equals q over 2d we get.
See the next equation. Example 4.19. Consider a point charge q inside a hollow, grounded, conducting sphere of inner radius A. Find A. the potential inside the sphere, B. Te induced surface charge density, C. the magnitude and force acting on a charge q. Solution A. Using the method of images we have the charge and its mirror appropriate to the spherical boundary condition giving a potential in the form. See the next equation. See the next equation. At x equals A, we have phi of A equals 0. Phi of x equals A equals q over A times the absolute value of n vector minus y over A, n vector prime plus q prime over the absolute value of y prime times the absolute value of n vector prime minus A over y prime n vector equals 0. This occurs when.
See the next equation. The potential is, thus, see the next equation. Let's consider a shift to explicit polar coordinates, where our radial position remains inside the sphere, i.e. r is less than a. So, let the absolute value of x vector equals r, the absolute value of y vector equals r prime, x vector dot y vector equals r prime cosine theta we then get for the potential inside the sphere. See the next equation. B. To get the induced surface charge density on the inner surface of the sphere we make use of the pillbox relation. See the next equation. We get, see the next equation. See the next equation.
Example 4.20. Consider a potential problem in the half-space defined by z is greater than or equal to 0, with Dirichlet boundary conditions at z equals 0 and at infinity. A. What is the Green's function? B. If the potential on the plane is v inside some radius, a, and 0 outside, centered at the origin of cylindrical coordinates, find an integral expression for the potential at a point P. C. Show the potential along the axis of the circle. D. Show that at large distances. See the next equation. Solution A. The Green's function is that of point source x vector prime with mirror source x vector double prime, due to B cease, such that.
See the next equation. And g sub d of x vector prime equals 0 for x vector prime at z equals 0 and at infinity. In cylindrical coordinates, ds squared equals d rho squared plus r squared d theta squared plus dz squared. This becomes, see the next equation. Using the result that see the next equation. And see the next equation. Thus, see the next equation. C, along the z-axis rho equals 0, so, see the next equation. D, at large distances rho squared plus z squared is much greater than a squared. We use see the next equation. To get, see the next equation.